In this video, we're going to be building on what we looked at in the light and Bohr model activity, and we're going to see a bit more about where the electrons actually are within the atom. Remember that the Bohr model did a great job of some things, but it didn't answer all of the questions that we will look at in this video. Previously, we looked at the Bohr model of the atom, and we also concluded that while it does a great job of this idea of quantization of energy, it really fails to fully describe what's going on for larger atoms. And so the answer is that it's not this orbit style picture that shows where the electrons are within the atom, but what we're going to call orbitals. And so what are the orbitals that are basically taking the place of n equals 1, n equals 2, n equals 3 is the whole story. So we still keep this idea of a principal energy level. So n equals 1, this is sort of the first of these general energy levels that can be accessed. And within this, we're going to have a single orbital that we name 1s. In the second principal energy level, n equals 2, we not only have an orbital that we're going to name 2s, but also we're going to have some 2p orbitals. And for now, I'm just setting up the pattern. We're going to take a look at some pictures of what these look like coming up. But the important thing is that there are some differences within each of these energy levels. In n equals 3, we have 3s, we have 3p, and we have 3d. And in the fourth principal energy level, we'll have 4s, 4p, 4d, and 4f. And again, just the idea of getting used to this pattern is what I'm really going for here. And it is to say that s orbitals are sort of the smallest, as we're going to see, and they begin at n equals 1. We introduce p orbitals at n equals 2. We'll see that this p sublevel is a little bit bigger. D orbitals come in at n equals 3. F orbitals come in at n equals 4. So what do these look like? So here's what an s sublevel looks like. And let's say this is 3s, 3p, and 3d. Whether it's 2p or 3p or whatever, we're going to have the same kind of picture. And the lesson is that in the s sublevel, we pretty much just have one orbital, right? There's the s orbital, it's this spherical kind of thing, and that's where we have space for electrons. In a p sublevel, we have three different what we call orbitals. And these are, areas that the electrons can be found in, basically. And so there's three different orbitals in the p sublevel, 5 different orbitals in the d sublevel. And so my question for you is that if each orbital should hold 2 electrons, and they do, how many electrons are going to fit within each of these sublevels? And so go ahead and pause the video here, see what you think, right? Remember that there is 1 orbital for s, 3 orbitals for p, and 5 orbitals for d. How many spots for electrons, therefore, can fit in each of these sublevels? Go ahead and pause the video and see if you can come up with an answer. All right, let's take a look. In the s sublevel, there is going to be 2 electrons, and in the p sublevel, there's going to be 6 electrons, right? 3 orbitals in the p sublevel. And finally, in the d sublevel, we're going to hold 10 electrons for having those 5 orbitals in the d sublevel. So this pattern where in s we have 2 electrons, in p we have 6 electrons, in d we have 10 electrons, maximum, we may not fill these completely, but that's the maximum amount they can hold, is going to be very important for moving forward here. And so when we look at the periodic table, right, the question is, when we have a given atom, where are those electrons located? And here on the left is kind of a useful little tool for showing what order we want to fill these sublevels in. So basically we draw up a little staircase, if you will. We've got 1s, 2s, 3s, 4, and so on. Remember that p orbitals don't show up until number 2. D doesn't show up till number 3, so we don't have any 2d or 1p or anything like that. So we draw up this little staircase and we do diagonal lines going downward. This shows that the first electrons are going to go in 1s, the next are going to go in 2s, then we go to 2p, then 3s, and so on. And it may seem like kind of a weird pattern, but this is the way that electrons are going to be filled. Now, this is also reflected on the periodic table because the different sections of the periodic table actually correspond to the different types of orbitals. And the different periods do correspond to different sizes of those orbitals, so different principal numbers for those orbitals. And this is shown on the periodic table as follows. This column on the side, this set of 2, we call this the S block, right? So basically hydrogen, lithium, beryllium, this set of two that are kind of over on the left, this we would call the S block on the periodic table. This is where the last electron we put is going to be in an S orbital. Over on the right, on the nonmetal side, that block of 6, that's the P block. For those, the last electron we place in is going to be in the P sublevel. For the transition metals in the middle, that's our D block and the little insert that goes to the very bottom where there's the elements that we don't talk about too much, but if you have something large, we do want to consider that that has F block electrons in it as well. So the thing on the left is a good useful tool for getting started, but do keep in mind that it can be even more useful to know the filling pattern off the periodic table. Okay, so where are the electrons located? We've talked about the filling order, and they're basically going to want to occupy the lowest energy orbital. They only really occupy a higher energy orbital because the lower energy spot is already filled. 2 electrons are permitted in each orbital, and once the subshell is full, the electrons need to go to the next highest energy, and we can see what the order of these are from the periodic table. And again, here's that picture. Jumping back to the periodic table, right, it looks like this. But if we show the blocks specifically, it looks something like this, which is showing, well, what is the sublevel that we're filling when we get to that spot on the electron, on the given atom. Okay, if we have oxygen, in other words, in its ground state, which is to say all the electrons in the ground state, which is most of the time what we're going to look at, we'd say, well, it's got 8 electrons. The first 2 go into 1s. That would be kind of where hydrogen and helium are. That's where the first 2 electrons go. So 1s2. The next 2 electrons go into where lithium and beryllium are. That would be 2s2. And as we're working our way up to the 8th electron in oxygen, we see that there are 1, 2, 3, 4 electrons to go to get for that 5th, 6th, 7th, and 8th electron. And that leaves us on oxygen. That's its 8 electrons. They're in 2p, and we place 4 of them because that's all we have, right? 2p could hold 6, but in this case, it's only going to hold 4 because that's our 8 electrons for oxygen. We call this the electron configuration for oxygen. Okay, go ahead and pause the video and see if you can do that on your own. I've just left the regular periodic table here, but if you want to go back and look at the one with the what orbital is being filled in each case, maybe that's helpful, but getting used to the idea of getting it from the periodic table, I think is really, really useful. So if you can, challenge yourself to that. I've left a challenging one here as well with calcium 2+. Remember, we're plotting the number of electrons, so I would first start thinking, how many electrons does calcium 2 have? Go ahead and pause the video and let me know what you come up with. All right, let's go ahead and take a look at the answers here. So again, this is the periodic table with those different blocks labeled more clearly. And for these ones, boron has 5 electrons, so we end up with 1s2, 2s2, 2p1. Sodium, 1s2, 2s2, 2p6, 3s1 is where we end. And for calcium, it's only got 18 electrons, so we don't make it all the way to 20 where calcium is. We end up with 1s2, 2s2, 2p6, 3s2, 3p6. Note that the filling order is kind of the same no matter what element we're looking at. We're just looking at how far up do we go to give the electron configuration. Okay, now beyond this, we can specify each of those electrons further. So with our electron configuration, we've shown where the electrons are, like how many there are in each of these sublevels, but we can actually further define each specific given electron with 4 quantum numbers. And the first one we've actually already looked at, right? The principal quantum number is a positive integer, meaning a number like 1 or 2 or 3 or 4 or so on. And this is basically that number within what sublevel we're filling. So if it's 1s, n equals 1. 2p, n equals 2. If it was 4d, n would equal 4. If it was, 6s, it would be 6, right? So it's that number within the sublevel. The second quantum number we'll call L, and that is an integer that depends on n. And this is basically the rule that tells us, well, only s is allowed in the first energy level, so the principal quantum number 1, n equals 1, only permits s. If it's 2, it permits s and p, and if it's 3, it can permit s, p, or d, and so on. So We're going to strictly assign this number to specific types of orbitals. If it's an s orbital, L is 0. If it's a p orbital, L is 1. If it's a d orbital, L is 2. And the number of L must go between 0. It can always be 0. This is to say we can always have s orbitals no matter what our principal quantum number is. And the largest it can be is 1 less than n. So if n is 2, the largest it can be is 1, which shows us why we don't have d orbitals. So again, these are rules. These are actually reflections of the actual quantum calculations that give shape to these orbitals. We won't get into that too much here, but for now, really just know that it indicates the shape of the orbital, which is whether it's sp, d, or f. Finally, or second to last rather, we have the magnetic quantum number, ml. This is an integer from negative L to L. So if L is 0, it can only be 0. If L is 1, it can be negative 1, 0, or positive 1. And this indicates the spatial orientation. Each orbital has a different ml number. So this is where we have 3 different p orbitals. There are 3 different options for ml. We have 5 different d orbitals. So there are 5 different options for ml. This again is reflecting a lot of the things we already know about orbitals. The last is that the electron within a given orbital can be either what we call spin up or spin down, value of positive 1/2 or negative 1/2. This shows how we can have 2 electrons maximum within each orbital. Okay, so let's take a look at this. This is what we call the orbital diagram for nitrogen. Each arrow here represents an electron. And we're going to say, well, what are these quantum numbers for each electron? Well, the first one, here in 1s2, right, we know n equals 1 because it's a 1s orbital. L equals 0. Again, s corresponds to L equals 0. ml can only be 0. There's only one s orbital in the s sublevel. And ms here for this one, it's pointing up. We'll call it positive 1/2. For the next one, right, maybe go ahead and pause the video here and see if you can conclude what the different quantum numbers for the downward arrow in 1s should be in this case. Remember, n corresponds to a certain thing. That's the number within the orbital that it lives in. L corresponds to something about the orbital, ml as well, and then ms is whether it's spin up or spin down. Go ahead and pause the video, see if you can get that, and if you want to try to get the rest of them, that's great on you too. All right, let's go ahead and take a look at all the quantum numbers for each of these electrons. Again, the idea is that these quantum numbers can provide specificity for every single electron within an atom. So the next one here, still n is 1, still L is 0, still ml is 0. So basically, n, L, and ml define the box that we're living in. And ms here is negative 1/2 because it's spinning down. Moving on, now we have 2s, so n is now 2, but L is still 0, that's an s orbital. ml is still 0 to indicate there's only one space available within the s sublevel. Plus 1/2 for the spin means it's spinning up, and we have the same options with minus 1/2 for spinning down. For 2p here, n is equal to 2, and L is now equal to 1. Remember that for p, L is equal to 1. ml here we're going to say is negative 1 for this space, and that it's spinning up. And note that n and L are actually the same for all 3 of these, and all 3 of these are spinning up, but what changes are these ml values. So one of these spaces we call negative 1, another we call 0, and the last we call positive 1. And this shows the 3 different spaces that are available for electrons to be in within a p orbital, or within a p sublevel. Each of these arrows represents a specific electron, and note that no 2 have the same 4 numbers. Every single electron basically has its own address that describe where it is within the atom. Okay, so as we're looking at orbital filling rules, it's important to keep a few things in mind as far as how we fill an atom and how we come up with an orbital diagram. So the first is one that we've already looked at before. The lowest energy orbitals are filled first, which is to say we fill 1s before 2s, before 2p, and so on, right? We put into the lowest energy orbitals first, and we use the lowest energy unoccupied orbital to continue. The next is that we want to maximize unpaired electrons. So in the previous example, we didn't pair up our electrons until we had them all half filled first. They like to sit alone in unfilled p orbitals, for example, and they want to spin in the same direction. So if the first one's spinning up, the next one wants to spin up, and the last one wants to spin up. If you chose to put them spinning down, that would actually be okay too, but then you want them all to spin down. Whether spinning up or spinning down, those are actually equivalent energy levels and energy states. And then finally is one that we've talked about already. Electrons all have their own address. No two electrons can be in the same place. No two electrons can have the same set of quantum numbers. Okay, that is actually quite a lot, right? We talked about orbital configurations or electron configurations, orbital diagrams, and these quantum number rules. So if it all sounded good, good on you. And again, while it may seem like this is adding more complexity to something that seems more straightforward, these are solutions to that problem of the Bohr model where we have interference from other electrons. These numbers are part of that solution and really do go with a lot of the rules that I think we can still know without knowing the quantum chemistry.